It's 8 o'clock for me. Welcome everyone to the One World Combinatorics on Words seminar. Today our speaker is Mickaël Postic. He just recently defended his thesis at the Camille Jordan Institute in Lyon. And he is going to speak about open and closed complexity of infinite words.
Okay, so hi everybody. So first, thanks to the organizers for having me. And as Nahad just said, I'm going to talk about open and closed complexity of infinite words. So this is a joint work with Olga Parshina we did last year. So the talk will be divided in 4 parts. So first, I will recall what the complexity function of the classical complexity function of a word is, and then I will say a few words about other complexity functions. Then I will define what open and closed words are, and I will define the complexity function associated to those notions. And finally, I will give an insight of the proof of the theorem we were able to prove with Olga. So first of all, the classical complexity function of a word is a function which counts the number of distinct factors of a given length in an infinite word. So let's look at some examples. So if we take the regular paper folding word, for example, we can count the number of factors of length 1 there is in this word. So you have 2 different factors, you have 0 and 1, and we can count the number of factors of length 2. For example, you have like 0, 0, 0, 1, 1, 0, and 1, 1. So you have 4 factors of length 2. And actually, it has been shown by Jean-Paul Alouche that the complexity of the regular paper folding word is 4n for every n greater than 7. If we take another very famous word, the Fibonacci word, we can easily see, I mean, it's not that hard to compute that the complexity function of the Fibonacci word is n plus 1 for every integer 1. Sorry. So you have like 2 factors of length 1, you have like 3 of length 2, etc. So a very famous theorem in combinatorics on words, I'm pretty sure all of you know it, is a theorem from Morse and Hedlund, which states that an infinite word is aperiodic if and only if its complexity function is unbounded. And moreover, it gives a bound on the complexity function for an aperiodic word. So some remarks on this theorem. The first thing is that the proof of this theorem is actually not that hard, and it relies heavily on the fact that the complexity function of a word is a non-decreasing function. And another thing that we can note is that the Fibonacci word attains the lower possible complexity for an aperiodic word. And the class of words satisfying this property are called Sturmian words, and they have like many interesting properties. For example, they give a link between combinatorics and word and number theory, and they are also used in interval exchange transformation. So since this theorem and this notion of complexity is really interesting, there have been the complexity function defined in other settings, like the abelian complexity has been studied quite a lot, but also has been the palindromic complexity or the cyclic complexity, and there are like many other which have been studied. The problem with all of those complexity functions is that they are usually not non-decreasing, and so you're not sure to find the theorem on Morse and Hedlund anymore. For example, if you take the Fibonacci word, we've seen that it's not ultimately periodic, that it's aperiodic, but the abelian complexity of the Fibonacci word is actually constant, always equal to 2. And if you look at the Morse word, if you compute the abelian complexity of the Morse word, you find that there are 3 different blocks from an abelian point of view of length 2, and you have like only two different factors of length 3, and you have only one factor of length 4 from an abelian point of view. Okay, now we can move to the definition of open and closed words and the complexity functions which are associated. So if you take a word W, we say that another word U is a border of W if it is both a proper prefix and suffix of this word. So if we take, for example, this word AAB, AAA, you can see that A appears here and here, so it's a border. And it's also the case for AA, which appears here and here as well. So we have that this word is bordered, and using the borders, we can define what a closed word is. A word is said to be closed if it admits a border which appears only twice, once as a suffix and once as a prefix in the word W. And a word which is not closed is said to be open. This terminology is due to Gabriele Ficci, and it's quite recent. And in a closed word, the longest border is called a frontier. So let's look at some examples. If you take the word AB, AAAAB, it is closed because you can see that AB occurs both as a prefix and as a suffix, and it does not occur internally. So it's a frontier. And now if you look at the word AABAB, it's open. So to see this, we just need to see that it doesn't have border, and that's the case here because you have like A and B, so you don't have a border of length 1. Then you can check the same thing for the length 2. So you have AA here and AB, so no border of length 2, and so on. And you find that it doesn't have a border. But you can also have some words which are bordered and are still open, and that's the case of the word we saw previously. So if you take this word, we've seen that AA is a border, but you can see that AR appears here already, which is not a prefix nor a suffix. So AABAAA is open. So some remark on the interest of open and closed words. So closed words have actually been quite extensively studied, and they are often called complete first return, and they do play an important part in symbolic dynamics because for recurrent words they give a new coding of the word. And if I remember well, last week one of the talk was talking about this so-called derived sequence you can construct thanks to the complete first return to a prefix. And so it was a good example of one of the use of closed words. Okay, now that we have defined open and closed words, we can define the associated complexity function. So the closed complexity function of an infinite word X is a function which counts the number of distinct closed factors of a given length n. And you can define similarly as you do with every complexity function, the open complexity function, which counts the number of open factors of a given length. So if we look at an example, if we take the periodic words of root A, B, B, A, we can check that the only closed factors of length 2 are AA and BB. So the closed complexity function of this word gives 2 to the letter 2, sends the letter the value 2 to 2, sorry. And you can compute that there is no closed factor of length 3 in this word. The factors of length 3 are going to be AAB, ABB, BBA, and ABB, and all of them are going to be open. And so if you look at the number of open factors for this function, for this word, sorry, you will have two open factors of length 2, which are AB and BA, and you will have 4 open factors of length 3, which are all of the factors. And something we can remark, which is true in the general setting, is that you will always have the number the total number of factors for a given length, which will be equal to the number of open factors for this length plus the number of closed factors for this length. And this is due to the fact that every factor is going to be either closed or open. So now the main result we were able to prove with Olga is the following. If you take an infinite word x, you have the following, which is equivalent. X is aperiodic, is equivalent to the fact that the lim_inf of the open complexity function is plus infinity, which is equivalent to the fact that the closed complexity is unbounded. So actually, this theorem is two Morse and Hedlund-like theorem, one in the case of the open complexity function and one in the case of the closed complexity function. So some remarks on this theorem. The first thing is that there was an equivalence in the theorem, but actually one of the direction is really easy to prove. And it's the fact that you have this, if you have the lim_inf of the open complexity function, which is plus infinity, then it's easy to see that x is aperiodic, because as I showed you on the previous remark, the classical complexity function is always greater than the open complexity function. So if the open complexity function is unbounded, so is the classical complexity function, and Morse and Hedlund gives the fact that x is aperiodic. And the same holds true for the closed complexity function. Another thing which is interesting with our results is the fact that because you have that lim_inf of the open complexity function equals plus infinity is equivalent to the fact that x is aperiodic, you get that a word as its lim_inf of its open complexity function is plus infinity is equivalent to the fact that the lim_sup of the open complexity function is plus infinity. So again, if you have the lim_inf which is plus infinity, of course the lim_sup is plus infinity. But if you look at in the other way, if you have the lim_sup which is plus infinity, then necessarily the classical complexity function is unbounded, so x is going to be aperiodic, and so the lim_inf is going to be plus infinity by our theorem. Finally, another thing that we can say on our results is the fact that we do have lim_inf in one of the case and lim_sup in the other setting. So the question is it possible to get lim_inf here as well? And actually, it's not possible to change the lim_sup in this equivalence by a lim_inf. For example, it is known that for the paper folding words, one have lim_inf of the closed complexity function is equal to 0. Okay, so now for the rest of the talk, I'm going to prove this theorem. So actually, I'm going to prove the results first for the open complexity function and then for the closed complexity function. So as I told you, there is only one direction which is complicated, and that's the one we are going to prove now. We are going to take a word which is infinite and which has bounded which has lim_inf of the open complexity, which is equal to k, and we are going to show that this word is ultimately periodic. To do this, we will mainly use one very efficient tool in combinatorics and word. I suppose probably most of you already know this, but I'm going to introduce a rosy graph of a word. So for an infinite word, the rosy graph of order n of this word is a graph whose vertices are the factors of length n, and the edges are the factors of length n plus 1. And there is a directed edge from u to v if there is a factor w of the word which starts by u and end by v. And as usual in a graph, in a directed graph, we can define the distance between two vertices as the length of the shortest path, the sort of directed path between them. But one thing which is worth noticing is the fact that the path in question does not necessarily correspond to a factor in the word. Okay, I'm gonna show rapidly on an example what I mean by rosy graph and what I mean by a path is not necessarily corresponding to a factor. So if we take this word A, B, A, C, A, C, A, D, 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 etc., and we try to construct its rosy graph of order 2, what we are going to do is we are going to read this word and check the factors of length 2. So you first have AB, so you put a vertex AB. Then you have BA, you put a vertex BA. Then you have AC, you put a AC. etc. So up to DD here. And now what you are going to do is you are going to read the word and look at the factors of length 3. So here you have like A, B, A. So it starts by AB and end by BA. So you have a directed edge here. And the same, you have like BAC, which start by BA and end by AC. So you have another one here, and so on. You have like ACA, so starting by AC, ending by CA. So you have this edge here, etc. And you can see that I forgot to put the DDD, which will give an edge from DD to itself. And know what I'm meaning by the fact that a path in the graph does not correspond necessarily to a factor in the word. If you look at this graph, you can see that the factor BA is distant from the factor AD with only distance 1, 2, 3. But the thing is that the corresponding path BACAD does not occur anywhere in the word. So what it means is that you can have two factors which are really close in the rosy graph, but which are always far away in the words. Okay, so with this, we were able to prove the following proposition, which states that if you take an infinite word and you look at its rosy graph of order n, and you take two factors which are closed and which are not too far away in the rosy graph, then you know that the size of the frontiers must be not too far away one from the other. Let's look at a graph, at a figure to illustrate this. So I'm writing first W1, which is here, and know that I know that W2 is at distance I in the rosy graph of W1. It means that you have this prefix of W1 which coincide with this suffix of W1 which coincide with the prefix of W2 of same length. Now what I can do is I can put the frontier of both of the words, and I know that U1 must not occur anywhere else in W1, and U2 must not occur anywhere else in W2 by definition of the frontier. So now if I look at this distance here, I'm saying that this distance must be positive. If it's not the case, what happens is that the first occurrence of U1 ends after the first occurrence of U2 ends here. So it would mean that U2 would actually end somewhere here, and it will be a factor of U1. But if U2 is a factor of U1, then U2 has to appear somewhere here inside U1. And it means that U2 has to appear somewhere here in the word W2. And this is not possible because, as I told you, U2 has to appear only twice, once here and once here. So we know that this has to be strictly positive. And actually the same holds true here. If this was negative, so if U2 was, if the second occurrence of U2 was starting before the second occurrence of U1, it would mean that U1 would be a factor of U2. So we would be able to find U1 somewhere here, and it means that U1 would be somewhere here. And this is not possible by definition of U1 as a frontier of W1. So this gives us this inequality here, which is like U1, the length of U1 minus the length of U2 must be smaller than I in absolute value. And what is interesting now is that if you take I to be equal to 1, then it gives you that the length of the two frontiers must be the same. So the interesting thing in that is that if you are following in your rosy graph a path consisting only of closed factors, all of those factors will have the same length of frontier. And if you remember that we are working with words which has only, which were on the rosy graph, you will find only a finite number of open factors. It will mean that most of the factors in this word would be in the rosy graph will be closed, and most of them will have the frontier of nearly the same length. Okay, so another lemma which is useful in the proof is the following. If you look at your word x, you know that you are not going to be able to find long powers of with long roots. And the reason why this is true is that since your word is aperiodic, if you take a very long power, at one point it must break, because otherwise the word would be periodic. And when you are going to look at the factors you get at the point it breaks, it is going to give you an open factor. And the reason why this is true is that if it was a closed factor, the frontier would be very long, because since you have the same word here and W here, you would have necessarily the frontier which must be longer than W, otherwise it would already occur in this part here, and the word would not, it would not be a frontier. So the thing is that this word is open, and now if you put anything you want after it and you delete the U1, you can do the same thing and it's still going to be open, and so on. So if you would find, if you add U power n with U big and n big, you would have a problem, because you would be able to construct a lot of open words that you don't want it. Finally, as I mentioned rapidly earlier, another thing that is true is that you will be able to, out of the closed word, will have frontiers of nearly the same size, and you can check that the size of those frontier must be long enough, at least for some length of in the word. And that is true because if it was not the case, then you would have a lot of frontiers, because you have a lot of closed words, so you would have a lot of frontiers, and and all of them would be nearly the same. So a lot of words would have the same frontier, and this would allow you to construct by overlapping some words. So this would allow you to construct long powers with short roots, and you don't want that. Okay, so now let's look at the sketch of the proof of the theorem. So the idea is the following: since your word is supposed to be aperiodic, for every length you are sure to be able to find a right special factor. So you are going to consider this right special factor, and you are going to look at the rosy graph and to construct two paths starting from this right special factor, and you stop this process as soon as in the upper pass and in the bottom pass you have a closed factor. So if you do this, you will be able to do it in at most k step, because you know that you have at most k open factors. So after at most k steps, you are going to find a closed factor on the upper pass and in the bottom pass. And those two factors, if you choose the initial n wisely, you can say that they both have very long frontier. So now you are going to look at the frontier and you say, okay, but since they have like very long common prefix here, those two words, actually the shortest border will be a prefix of the longest border. And it's not exactly true for that it's a suffix of the longest border, but up to a little modification, it's true as well that it's a suffix of the longest border. So finally, what you get is you get a border which is overlapping itself a lot. So this allows you to construct, again, a long power with short roots, and you don't want that. So this proves the first theorem we had. Now we can move to the case of the closed complexity function. So what we want to prove is that words with bounded closed complexity are ultimately periodic. So you take x such that you have the lim sup of the closed complexity, which is smaller than an integer k, and the theorem we it says that x has to be ultimately periodic. So the most important lemma we add in this is this following lemma. So it's quite ugly, but I'm gonna explain it a bit. So first of all, you have this rec fact here, which means the set of recurrent factors. So the recurrent factors are the factors which appears infinitely often in the word x. And so what the what the lemma says, it says that whatever the recurrent factor you are considering, you know that there will be a left extension which will be left special in at most k step, or you know that for every recurrent factors, you will be able to find right extension which will be recurrent and which will be right special. Okay, so let's just show the idea of the proof. So if we suppose that it's not the case, you can find a factor which is recurrent and which will always be preceded by the same thing, a1, a2, ak. Every time you are going to see it in the word, it's going to be preceded by this. And you can also suppose that you can find a factor v, which has the same thing, but on the right. So it's always going to be followed by b1, b2, bk. And now what you can do is you can take w such that uwv is a recurrent factor of x. So this is always possible if u and v are recurrent. And now you can consider complete first return to uwv. So the situation will be this one. So you have uwv, sorry, then something, then uwv, and you know that uwv does not occur internally. And now, since you are in your word, you know that before this, you will always find a1, a2, ak, and after this, you will always find b1, b2, bk. And that's also the case internally. Like after this v here, you will always find b1, b2, bk. So you have b1, b2, bk here. And since before the u here, you always have a1, a2, ak, you can be sure that here you have a1, a2, ak. Okay, and the thing is that this is not possible because this would allow you to construct too many closed factors. And indeed, this factor here, starting in the a1 here and ending in the end of the v here, is a closed factor, because if you look at the frontier, I mean, if you look at the prefix a1, a2, which ends in the end of v here, it occurs both as a prefix and as a suffix. And I'm saying that it's not occurring internally, because if it was occurring somewhere in the middle, then you would need to have uwv somewhere in the middle, but we chose the word to be such that uwv does not occur in the middle. So, okay, you know that this word is closed. And now what you can do is you can look at the word starting with a2 and ending by the b1 here. And this word will have the frontier a2 up to b1, because you will have the same thing here. And for the same reason, it does not occur internally, because you still don't have uwv somewhere in the middle. So that's the idea. And that allows you to this lemma allows you to say that, okay, so either for every factor, you will frequently branch to the right, or for every factor, you will frequently branch to the left. So without loss of generality, in the rest of the proofs, I will suppose that you can find a factor which frequently branch to the right. That for every factor, you will frequently branch to the right. Sorry. So a corollary of this lemma is the following. If you take an infinite word with bounded complexity, which is recurrent, uniformly recurrent, sorry, then it has to be periodic. So why is that true? Well, you can always consider a very long factor v of this word x. And the idea is that if you consider a well-behaving enough factor of x, you can be sure that you can construct a word as long as you want, which avoids u. And this is not possible because which is a factor of x and which avoids u. And this is not possible because x is supposed to be uniformly recurrent. So you're supposed to see u quite often in x. But the idea is that by applying the branching lemma we just get previously, you can avoid to see u again. And the idea is the following: you go to the first branching point, which happens after at most k step, and you choose the branch which allows you to stay as far as possible from constructing u. And then after that, you will do the same at the next branching point, and so on and so on. So in the end, you can construct a very long factor of x, which avoids u all the time. And this is not possible in a uniformly recurrent word. So it means that the previous lemma is not applying. So it means that the only possibility is that x is not ultimately periodic and is not aperiodic. And for a uniformly recurrent word, being ultimately periodic and being periodic is the same thing. So you know that x is periodic. Okay, another lemma we need is the following, and it's a bit like previously. It states that you know that you, if you have a word with a closed complexity function which is bounded, then you know that you are going to avoid having long powers with short roots. And why is it the case? It's because if you take a square, then this word will contain all of, if you take a cube, sorry, then this word will contain all of the squares of rotation of the roots u, and all of the words of this type are actually closed because they are closed with a frontier r of u, rotation of u, where because every square with primitive roots is always closed with the border, with frontier the root. Okay. So now another tool that I need is the shift of closure of a word. So I'm just gonna define it, but I think most of you already know this as well. So the shift operator, I'm sure this one, all of you know it. It's the operator where from a word you get t of x by deleting the first letter of x. And the shift orbit closure is the closure under the usual topology of the set of the orbits under the shift operator of a word, of the word. So what interests me actually in the shift orbit closure is that every word in the shift orbit closure of x has a set of factor which is a subset of the set of factor of x. So this is very interesting because if x has a bounded close complexity, that's going to be the case for every word in the shift orbit closure of x as well. And the theorem I'm going to use in the rest of the proof with the shift orbit closure is that every word x verifies the property that its shift orbit closure contains at least one uniformly recurrent element. So now what is the sketch of the proof in this case? So you take an aperiodic word x which has a bounded close complexity, and you first construct a word y which does not contain powers of great order. So I'm not precising what great order is here, but the idea is that you can do this using the branching lemma, because you can avoid constructed long powers by applying the branching lemma that you have. And you know that you just have a finite number of words which occurs with great power by one of the lemma I showed you previously. So you just have a finite number of patterns to avoid with your branching process. So this is possible. And then what you do is you take this element y, which still has bounded close complexity, and which cannot be periodic because it does not contain powers of great order. And we consider a uniformly recurrent element in its shift orbit closure. So since it's going to be in the shift orbit closure of y, it will still have bounded close complexity. And the thing is that because of one of the theorem we saw previously, this means that since it's uniformly recurrent and with bounded close complexity, it must be periodic, but then it would contain powers of great order, and then y would need to contain powers of great order, and this is not possible. So, okay, this is the proof. Now I would like to state it in the actually a bit more general way we were able to prove it. So without changing much the proof, we were able to prove it in the case of closed complexity bounded in synthetic sets. So what is a synthetic set? A subset of n is said to be synthetic if it doesn't have like two wide gaps in it. So if it verifies this property for an integer d. And the theorem we were actually able to prove was the following one. It was that if you take a word such that there exists a synthetic subset on which the closed complexity of this word is bounded, then this word has to be ultimately periodic. Okay, so in conclusion, what we were able to prove was the following. If you take x, an infinite word over an alphabet A, you have the following which are equivalent. X is aperiodic, the lim_inf of the open complexity function is plus infinity, and there exists a synthetic set such that the closed complexity is bounded on S. So this gives you like two Morse and Hedlund like theorems. And thank you all for your attention.
Thank you very much, Mickaël. Does anyone have any questions?
I have a question.
Yeah.
It's known that the ordinary subword complexity function is what's called synchronized for automatic sequences, which means that there's an automaton that will read n and the subword complexity function, let's call it f of n, in parallel in base k, and it will recognize that set of things.
Okay.
And this is also known, I think, for some other things like the number of primitive words of length n that appear as factors, and a few others. But then there's some that it's provably not synchronized. So your nice talk caused me to think, well, is this number synchronized for automatic sequence? Did you ever look into that or hear about, did anybody study that?
I did not look on this, and I would be surprised because we looked at the behavior of the closed complexity function for some words, and it's sometimes like kind of odd. So I would be surprised, but that would, I mean, I did not really look at it. So
yeah, I agree with you. I think it probably isn't, but try to, if you have some good candidates where it's really odd, send them to me and I'll try to think about it. Yeah.
Okay, with pleasure.
So thank you for your talk.
You're welcome.
Anyone else have a question?
Hi, thank you very much for the talk. So I was wondering what happens for B-infinite words.
I haven't looked at B-infinite words, so I don't really know. I suppose that most of the part of the proofs, like, you know, the lemma, which is really important about like rosy graphs, I think you can have the same in B-infinite words. So I think, I mean, in this, I'm kind of confident that you would probably be able to get results a bit the same kind of result, because this thing doesn't change in B-infinite words. So I think it should be possible to extend it to B-infinite words, but I haven't looked at it.
Thanks. And maybe even more tricky, would there be a similar definition for two-dimensional words? I mean, it looks quite hard to define, but maybe there is an easy way.
I don't really know. Okay. I don't really know.
Yeah, thanks.
You're welcome.
Any other questions? All right. If not, I guess we will stop a little bit early today. Thank you, everyone, for coming. And our next seminar will be in 2 weeks, on March 15th. All right. Thanks, everyone. I'll see you in 2 weeks' time.
Thank you.